Hi everyone. Pre-calculus 1.3 continuity and the behavior and the limits. Okay, so we'll talk about these topics here. Limits. So the way we denote the limits is following. The way you read it, limit of f of x as x approaches c is equal to blah blah. In this case, they said L. Okay, what does that mean? Let's say there's a graph of f of x. There's a value of c for x. So as x value on this graph approach to c value. So you can approach c value from both directions. You can approach c from the left. You can approach c from the right. You can approach c value on the graph from the left. You can approach c value on the graph from the right. And in this line, as x value get approach to c value, y value is approaching to L. So that's a conceptual definition of limits. So like in this curve, as x limit of f of x as x approaches c is L. So c value for x is here. So x value approach to c, x value approach to c from left and right direction, and y value is approaching to whatever this value is, which is L. So very important statement here. The limit at any x value, the limit at any x value will only exist if the function value is approaching the same number from left and from right side of the x value. Limit only exists if approaching to the left, from the left, approaching it to from the right, if that approaching value of y is the same. X from the left hand, from right hand, that approaching values match, then only then limit exists. Finding limits. A limit is the y value of a function approaches as x gets close to a particular value. So we can ask you, limit of f of x as x approaches to 1. So on this graph provided, value of x is 1. Where? Right here. That's value of x equal to 1. So x approach to 1, you can approach 1 from left-hand side. So x value is 1, approach 1 from left-hand side on the graph. What y value is approaching to? Y value is approaching to 0 from left-hand side. Well, if you approach 1 from right-hand side, here's a graph. So x is approaching to 1 from right-hand side. What y value is approaching to? Well, y value has been straight constant here all through 1. So as x approaches to 1 from right-hand side, y value is approaching to 1. So left hand approaches to 0, right hand approaches to 1. So left, right limit, they do not match. That's why we don't have limit, does not exist. Limit of f of x as x approaches to 2. So x value is 2, look at it, where's the 2? 2 is right here. So limit of f of x as x approaches to 2 from left-hand side, you trace the graph from the left. What y value is approaching to? 1. 1 here. Approach 2 from right-hand side, what y value is approaching to? Approaching to 1. Left-hand limit, right-hand limit, they do match as 1. So that's why limit value is 1. Limit of f of x as x approaches 3. So 3 is right here. So approach 3 from left, approach 3 from the right. both of them is approaching to true, so limit value is 2. Continuity at a point. Any function whose graph can be sketched on one continuous motion without lifting a pencil is an example of continuous function. So if you can trace a whole graph without taking your pencil off from the paper, that means they are continuous. Continuity at a point and on open interval. So the figure below identifies 3 values of x at which the graph of f is not continuous. So if you look at this curve here, there's a hole here. Hole means there's no function value. So you can trace the curve here with your pencil, but you get stuck right here. There's a hole. You cannot move to the other section without making that color. So since there's a hole, you got stuck here. You cannot continue tracing the graph to the right hand side. So it's discontinuous at this point. Value of x as a 2. C, I mean. X equal to c, it's discontinuous. But here, continuous, it's all solid curve. Continuous everywhere here. But it's not continuous at x equal to c. Okay, this example, if you look at it, limit of f of x, x approaches c does not exist. What are they talking about? Okay, right here you can trace graph here, but you get stuck here. You cannot move on to here without taking a pencil off from the paper. Otherwise, you will have to like draw another line there. So they are discontinuous here at x equal to c. And if you look at it, x equal to c, you approach c from the left-hand side, you approach c from right-hand side. The limit, left-hand limit, right-hand limit do not match in this example. Okay, continuous. So if you look at it here, continuous, just like this example, there's a hole here. So you cannot continue to move on to the other side. So this is discontinuous at this point. The difference of these two graphs are, there is a function value defined at x equal to c. So f equal to c, we do have a function defined. Here, f equal to c, function is not defined. That's the difference. But discontinuous wise, yeah, it's not continuous here. It's not continuous here. Okay, it's called a continuity test. So it's pretty easy for us to tell continuous, discontinuous when graphs are available. You just look at the graph, it's pretty simple to tell. Well, algebraically, how do we verify it's discontinuous or continuous? It's called a continuity test. And you need to memorize this 1, 2, 3 condition. The function f is continuous at x equal to c if it satisfies following conditions. So function f of x is continuous at x equal to c if it satisfies condition number 1, condition number 2, condition number 3, all of it. If any of the condition is not satisfied, then we cannot say function f of x is continuous. F of x is defined as c, which means f of c exists. F of c exists. First condition. F of x approaches the same value from the either side of c, that is, limit of f of x as x approaches c exists. Limit exists. Second condition. Third condition. Function value and limit are equal to each other. So result from number 1, result from number 2 are equal to each other. So the value of f of x approached to from each side of c is f of c. So limit value, function value are equal to each other. It's called the continuity test. So let me come back to this. When I ask you, let's say there's a graph like this, and if I ask you, show that x equal to c is discontinuous, or show that x is continuous or discontinuous at x equal to c using continuity test, this is what you have to do. You have to check first condition. F of c exists. So you look at it, f of c exists. F of c is not defined. F of c, when x equal to c, there's nothing there. So for first graph, first condition is busted. F of c does not exist, discontinuous. Done. Let's say I ask you to do continuity test with the second example. Then you have to start with the first condition, f of c exists. F of c exists. When x equal to c, there's a function value? Yes. F of c does exist. Whatever this value is, let's say that is whatever the value, for example, let's say that was a 5. Then you can say f of c is 5. Then you move on to second condition. Does the limit exist as x approaches c? And you see x approaches c, then limit, left-hand limit, right-hand limit do not match. So you say, limit does not exist. So for this graph, you will pass first condition, but second condition, you will fail. You say, limit does not exist, discontinuous at x equal to c. What if you are asking, you are asked to do continuity test with this example? So again, you start with the first condition, f of c exists. Looking at x value as c, is there a function value? Yes, function value, whatever this value is, let's say it's like 2. F of c is equal to 2. Then you move on to second condition. Does the limit exist as x approaches to c? As x approaches c, left-hand limit. As x approaches c, right-hand limit. Do they match the same value? Yes, whatever that value is, let's say that's a 4. Limit does exist as a 4. I'm just making a number. So then you pass the second condition, then you have to check third condition. Does the limit equal to function value? So function value is this. I said 2. Limit value here is this, which is 4. Is 2 equal to 4? So that's third condition which violates. So it's a third condition. Limit does not equal to function value. So discontinuous. Okay, use the definition of continuity to determine if the function is continuous at which of the following x values justify each answer. So x equal to 0, x equal to 0 is right here. So if you look at it, it's a solid dot, x equal to 0. So we say, yes, it's continuous. X equal to 4, it's at the end, x equal to 4 is a solid dot 2. We say, yes, x equal to 0, x equal to 4, it's a continuous. Because it's all solid dot and one side of the limit. So as you can see, there's no left-hand limit here. It's not even there. So only one side of the limit. So from the right-hand side, from left-hand side for these points, we say they are continuous. So it's fairly easy to say. So when you look at the graph, continuous, continuous, it's going to be discontinuous here. Continuous, continuous, it's going to be discontinuous here. Continuous, continuous everywhere else, just by looking at the graph. Okay, x equal to 1. But they want you to use the definition of the continuity. X equal to 1. 1. So you have to be very careful with the continuity test. This is condition 1, 2, 3. You have to go through. So x equal to 1. First condition. F of c exists. So you look at it, 1, f of 1 exists, yes or no? Yes, f of 1 is defined right here. F of 1, solid dot here, f of 1 is 1. So first condition is satisfied. So I say x equal to 1, condition 1 was f of c exists. So f of 1 exists, which was 1. First condition, check mark. Second condition was limit. Does limit exist? So limit x equal to 1 as x approaches 1 from the left, as x approaches 1 from the right. They don't match. So limit of f of x as x approaches to 1 does not exist. Busted right there. So that's why it's not continuous. Not continuous at x equal to 1. So I did the first condition. I was doing second condition, busted. Right then, you just stop right there. Instead, not continuous. Because left hand, right hand limit doesn't. So limit does not exist. X equal to 2. So x equal to 2. It's fairly easy for you to say this discontinuous by looking at the graph, but using discontinuity test, x equal to 2. So f of 2, does f of 2 exist? At f of 2, x equal to 2, function value is defined at 2. Yes, it does exist. Check mark. Limit of f of x as x approaches to 2. So 2, approach 2 from the left, approach 2 from the right. Do they match? Yes, they do match. What's the y value then? 1. So yes, they do match as 1. So that was second condition. Third condition, the answer for 1 and 2, function value and limit value, do they match each other? So this was 1, this was 2, so you say limit of f of x as x approaches to 2, is that equal to f of 2? Busted. We say not continuous at x equal to 2 because third condition is not satisfied. X equal to 3. So x equal to 3. Again, just saying by looking at the graph is fairly simple. It's all continuous here. So you say, yeah, you know it's continuous. But checking by definition of the continuity, you have to check these three conditions. So first one, function value, f of 3, when x equal to 3, what's y value? 2, right here. Limit of f of x as x approaches to 3. So on this graph, approach 3 from the left, approach 3 from the right, what y value is approaching to? 2. Third condition is, are they matching each other? Limit value, function value, are they matching each other? Yes, they are matching 2 and 2. So you say limit of f of x as x approaches to 3, is that equal to function value f of 3? Yes. Check, check, check. And we say continuous at x equal to 3. Okay, there are three types of discontinuity. First one, it's called infinite discontinuity at x equal to c. So this function value increases, this function value decreases. So this is x value to c. So left hand keeps going down, right hand keeps going up. Of course, there's no function value defined here. And you have discontinuity at x equal to c. We call that as infinite discontinuity. Okay, this discontinuity happens at rational function. Rational function. So x in the denominator, that's when this could happen. Jump discontinuity usually happens at piecewise function. Piecewise function, Usually it happens a piecewise function. Jump discontinuity, you have to jump. So you know x equal to c, this graph is discontinuous. Removable discontinuity. So this one can also happen in rational functions. Rational functions. So graph has a hole somewhere. So it's a discontinuous at x equal to c. But why do you say removable discontinuity? If you just color that one hole, then it becomes continuous everywhere. So you can remove it by just coloring one point. So we label that as a removable discontinuity. Okay, it's very important for you to understand the situation of all these three. Okay, these two can happen rational functions. This one happens as piecewise functions. Okay, so if you have a piecewise function, you're dealing with a discontinuity. Most likely, if you have discontinuity, you have a jump discontinuity. And just make sure, does the function value exist here, x equal to c? Yes. But as x approaches to c value from the left-hand side, as x value approaches c from the right-hand side, they do not match. That's why the limit does not exist, so it's discontinuous. You have to look at how to tell whether it's an infinite discontinuity or removable discontinuity. So let's take a look at it. When x equal to c, is a function defined? No, f of c does not exist. What about here? F of c does not exist? It does not exist either. Let's look at the limit. As x value approaches c from the left-hand side, x value approaches from the right-hand side, the value will be quite different. So one side will be like very high value, one side will be very low value. That's how you know. Also, if you approach closer, this value will keep increasing. As you get closer to C, this value keep increasing. As x value approaches C from the left-hand side, this value will keep decreasing. So that's one thing you have to think about it. When you look at this, removable discontinuity, left-hand limit, right-hand limit will approach you to same value. So it will keep increasing as well, but not so much. Let's say this value is, for example, like 3. Value y is, let's say, limit value is 3. As you get closer to C, you will get closer to 3. So like 2.9, 2.999, 2.9. At a certain point, your calculator say 3. Same thing, as you go approach to here, you will say 3.01, 3.001, 3. So it will be very, very close to 3 value. Here, it's going to keep getting up, it's going to keep going down as you get closer.